Okay, so, all right, so now we're in business. So let me bring this up. All right, so let's talk about chemistry. Hope you guys are looking forward to this. So, what is chemistry? Let's deal with that question first. So, chemistry is that area of science which deals with matter. We're going to define what matter is later on. But basically, chemistry deals with, as you can see here, three main things about matter: the composition, structure, and properties. And then, in addition to that, we're not just concerned with and reactions, I should say, in addition, right? So you have composition, structure, properties, and reactions. And what we're trying to understand in chemistry is how the composition, structure, and properties relates to the changes that we observe for matter. And in order for us to do that, we have to look at matter in terms of what happens at the microscopic level, right? So we're talking about atoms at the level of atoms and ions and so on, molecules and so on, all right? So that's what chemistry is, all right? So at the heart of chemistry is matter. What is matter? Matter is anything that has mass and volume. Anything that has mass and volume is matter, right? And that could be anything solid, like ice, anything liquid, like water, anything gaseous, like water vapor, all right? So as I said before, in chemistry, we're concerned with several aspects of matter. One is a composition, right? What do we mean by composition? We're talking about the makeup, right? The different elements that come together to make up the particular substance. And we're concerned with not only the fact that we have different elements, but the relative amounts of elements that are present. So for example, to use a simple example, water is made up of two elements. One is hydrogen and the other one is oxygen, right? But we can talk about the composition as well in terms of the proportion of hydrogen atoms to oxygen atoms, which would be 2 to 1, right? And we can also talk about the composition with respect to mass, right? What you'll find is that in the case of water, the mass of oxygen is about 88%, and the mass of oxygen in water is about 88% percentage-wise, and then for hydrogen, it's about 12%, all right? So as you're going to see later on, when it comes to different compounds, we're concerned with the composition as well, because of course, you can have two or more substances that have the same elements, but the compositions will be different, right? So in order for you to make a distinction between those substances, you need to identify what their compositions are. The other aspect of matter that we're concerned with is structure. When we're talking about the structure, we're talking about how the different parts, the particles, the atoms, and so on, how they're put together, right? So for example, again, using the water example, water consists of, as I said before, 2 hydrogen atoms and 1 oxygen atom. And if you were to look at the structure more closely, what you see is that you're going to have the oxygen atom connected simultaneously to each hydrogen atom, right? So basically that would be the structure of the water molecule, all right? And there are other aspects of structure as well, because we're not only concerned with connections, we're also concerned with, in some cases, the actual shape of the molecule. Because as you're going to learn much later on, I think this will be chapter 14, you're going to learn that the shapes of the molecules can have some influence on the properties that are displayed by the particular substance, right? And for those of you, especially if you plan to go as far as organic chemistry, you're going to see how shapes of molecules can have a profound effect on the chemical and physical properties of a particular molecule. The other aspect of matter that we are concerned with in chemistry, I mentioned in passing, and that would be the properties of the substance. So in chemistry, and to a lesser extent in physics, when we talk about the properties of a substance, we're talking about those defining characteristics, all right? So in the case of water, I can say, for example, water has a boiling point of 100 degrees Celsius, has a freezing point of 0 degrees Celsius. It is colorless, tasteless, what else? Density of 1.00 grams per mil, right? All that I've just mentioned are basically mentioning different properties of water, right? These are all the defining characteristics of water, right? And what you'll find is that different substances will have a different set of defining characteristics or different properties, all right? And then finally, we're concerned with the reactions, right? So the reactions, of course, are the chemical changes that substances will undergo. And we try to understand the reactions in terms of all the other characteristics that we just discussed, composition, structure, and properties, all right? So that's basically what chemistry is all about, all right? So the next slide is one of my favorite pictures because, of course, being a chemist, I'm biased. I think chemistry is the most important science there is. And, we in the science department, chemistry folks, physics folks, biology folks, we tend to banter with each other to say, who has the most influential discipline, whatever. And of course, chemistry always wins out in terms of this discussion. And the main reason why is because chemistry literally influences all other disciplines, right? And that is demonstrated in this diagram right here, all right? So basically, if you're doing physics, there's a little chemistry involved, right? Believe it or not. In fact, in all sciences, medicine, toxicology, biochemistry, pharmaceuticals, engineering, nutrition, what else? Electronics, materials, all that good stuff, all scientific stuff, all tech stuff, chemistry is involved to some degree or another, all right? And not only is chemistry involved in other sciences, but even in non-science disciplines, right? Such as law, let me see what they have here, education, and so on, all right? So in my opinion, and I'm very confident in saying this, chemistry is the central science. Chemistry is the most important science. You pretty much cannot have any other science discipline without chemistry, right? So that's the reason why, for example, if you plan to major in any of these disciplines, you must encounter some chemistry course along the way, all right? If you're doing medicine, you need to do chemistry up to, if I'm not mistaken, I think you guys would have to do up to molecular biology, which is basically, I could argue that that's biochem. If you have to do engineering, and I guess depending on your engineering field, you'd have to do chemistry up to, I think, either general chemistry 1 or 2, or organic chemistry if you're doing chemical engineering. Last I checked, I don't know if things have changed since then, right? So this is just basically underscoring the fact that chemistry is the most important field, and that's the reason why you have to do it. Okay, so let me take a bit of a departure or detour, and let's talk about the scientific method. This is the method that is used by scientists to basically explain what is observed in nature. And there are several steps that are involved in the scientific method, which we're going to discuss right now, right? So the first step involves defining the problem by recognizing it and stating it clearly, right? So basically, it all depends on your discipline. It all depends on what you're researching. Once you define it, that would be your observation. So basically, you'll be using your senses to basically observe, right? What you see, what you smell, etc. So observation is the first step. And then the second step is that you put forward a tentative, kind of speculative explanation for what you observe in the first step, all right? The name we call this a hypothesis. Now, the hypothesis have to be reasonable, has to make sense. You cannot just come up with any story, right? But it's something that is reasonable in terms of explaining what you observed in the first step, right? This basically is going to be tested in order for you to do the next step, right? So you're not just satisfied with coming up with an explanation. You want to see if that explanation can hold up to testing, right? Now, in the natural sciences, the way we test a hypothesis is by conducting or performing, well, firstly, you'd have to design the experiment and then you conduct the experiment, right? So the experiment that you're going to come up with, the experimental design, must be such that it will basically knock down the hypothesis if the hypothesis is not true, right? So you have to design the experiment in such a way so as to test the hypothesis, right? And then you perform the experiment, right? And then after the experimentation, what you'll find, especially in the preliminary stages, what you'll find is that the information that you'll get from your initial experiment will not fall in line with what the hypothesis predicts, right? So what does that mean? That means that you have to go back to the hypothesis and do one of two things, right? You either have to refine the hypothesis, which in other words, change the hypothesis so that it fits the data, and then, well, not and then, or come up with a different hypothesis that fits the data, all right? After that, you test it again. You test the new hypothesis, right? And what you'll find again is that you'll have to basically repeat the testing because, again, the data might not coincide with the new hypothesis, which means you have to go back to the refined hypothesis, change it or replace it with another one and test it again. So as stated here, you're going to repeat steps 3 and 4 repeatedly until you get to a point where the hypothesis successfully predicts what will happen. In other words, there'll be an alignment between your resulting data after repeated testing and your refined hypothesis, all right? So basically, when you observe that consistency, that observation we now designated as a scientific law. Basically, a scientific law is a statement of what is observed for which there's no exceptions, all right? Now, the refined hypothesis, which is backed by the weight of the data as a result of repeated experimentation, we call that now a theory, right? So it's very important that you understand the difference between a theory and a hypothesis, right? Because as stated here, a theory is an explanation which is backed by the data that is gleaned from repeated experimentation, right? While the hypothesis is an initial tentative explanation that you put forward to explain your observations, right? So that's the difference between those two, right? So that's a theory, which is backed by the weight of the data arising from the experimentation. So this is a flow chart, basically, which shows you what I just discussed, right? So as I said before, you have your observations, and then you put forward a hypothesis to explain your observations, and then you conduct an experiment, right? And then, as I said before, initially, the data that you get from the experiment usually will not line up with what the hypothesis says or predicts. So you'd have to come back here and either change your hypothesis or come up with a new one and do your some more experimentation. So this process is repeated over and over again until the data from the experiment lines up with the refined hypothesis, and that refined hypothesis is now the theory, all right? As I said before, the theory is the explanation based on the data from repeated experimentation, all right? And can successfully predict other things too, all right? Now, what I did not mention before is this last step right here, all right? Where it says further experimentation, because what you'll find, and there's a lot of examples in the history of science where this is true. What you're going to find is that if you look at scientific history, you can have a theory which was established and believed by all the experts, the scientific experts and so on. And the theory might be around for, decades or even centuries, right? And then a person on his own, tinkering in the lab, may test the theory and basically using, whatever technology that he or she might have at the time, and find out that the theory could not stand up to the testing that he did, which means that what? We discard this theory, because any evidence that one can get to contradict any established theory basically renders that theory useless, pretty much, right? Because now we have experimental data that contradicts that theory. So what does that mean? That means that we have to do further experimentation, right? Which is basically a repeat of this step right here to end up with a new theory, which would line up with the data provided by the further experimentation, right? And as I said before, there are several examples of that happening. But before we get to that, let me go back and reiterate definitions that we talked about before, because I think it's very important, especially when it comes to these three terms, that we understand the difference between them, right? It's very important that you understand the difference between a hypothesis, a theory, and a law, right? Very important, because I've even seen in textbooks and in other chemical literature where scientists have, made the error of mixing up one with the other, all right? So the hypothesis is, as I said before, a tentative explanation that is put forward initially to explain whatever was observed initially, right? That is the hypothesis. So therefore, it's kind of like a speculation, you did not do an experiment, you did not get any data to get to the hypothesis. You just come up with an idea, which makes sense, right? It could be true, but of course, it's not something that you can really accept because there's no data behind it, right? So that's the hypothesis. And as stated here, the hypothesis, in fact, forms a basis for further experimentation, right? After repeated experimentation where the hypothesis is refined or even replaced, then we end up with what is called a theory, which is basically an explanation that is backed by the weight of the data and information that is obtained as a result of repeated experimentation, right? So that's the main difference between a hypothesis and a theory, right? The hypothesis is an explanation which is speculative, no data behind it, right? But the theory is what is obtained. It's a model that is based on repeated experimentation, all right? And then we have the law. The law is basically a statement of what is observed, a natural phenomenon of what is observed, right? For which there are no exceptions, all right? So key thing you need to remember here when it comes to the law is that the law is not an explanation, right? The explanation actually is this right here. Actually, there are two explanations, but this here would be the one that's accepted, the theory, because it's backed by the weight of the data. The hypothesis is a tentative explanation, but the law is not an explanation. The law is basically what you observe. Like, for example, one law that you're going to meet later on, I think in chapter 13, right? In this course, is Boyle's law, right? Boyle's law is a law which relates the pressure of a gas to its volume. And basically what that law says is that the pressure of a gas is inversely proportional to the volume. What that means basically is that if you reduce the gas volume by a half, then the pressure of the gas in that container would be increased by 2, right? So you have that inverse relationship between the two, right? So Boyle's law basically is stating what is observed. Boyle's law does not explain why the pressure increases when the volume decreases. Now, there's a theory that explains that, which I won't get into right now, but we're going to get into it when we get to chapter 13, and that is the kinetic molecular theory. And that goes into the details in terms of how the particles behave, and therefore, based on how the particles behave, you can understand why the pressure of a gas is increased when the volume decreases, right? So that's just one example demonstrating the difference between the law and the theory. The law is not a theory, the law is not an explanation, the law is basically an observation that you make, which happens every time without exception, all right? The theory is just an explanation based on the weight of the data that is used to obtain the theory, all right? And this is just a side-by-side comparison of the hypothesis and the theory, again, stressing the difference between them. The hypothesis is a tentative explanation, while the theory has considerable evidence or facts to support it, all right? So very important that you're able to make the distinction between the hypothesis and the theory in the scientific method. Now, believe it or not, in your everyday life, you have actually, without realizing it, employed the scientific method to solve your daily problems, all right? So I'm just going to use one example here, and I'm quite sure you can think of other examples from your everyday experiences, right? So let's say you want to play your favorite CD. And I know I'm kind of dating myself because I don't think you guys use CDs anymore. Maybe I'm wrong. But anyway, let's say that you want to play your CD and you put the CD in your CD player and the CD skips, all right? Now you really want to listen to your CD, so you have to solve this problem. How are you going to be able to listen to your CD without this issue, right? Now, in the scientific method, that would be your observation, all right? So what's the next step in the scientific method that I mentioned before? Yes, sir. Testing, all right. So basically, you have to carry out a test to figure out, okay, what's wrong with your, but before you get to the test, there's something else.
Hypothesis.
Hypothesis, thank you. Right, so the testing will come later, but hypothesis first. So the hypothesis is basically, as I said before, a tentative explanation for what you observe. So my question to you is, what would be the reason or possible reasons, because you can have more than one, what would be the possible reasons why the CD does not play in a CD player? Why is it that the CD skips? Yes, sir.
Yeah.
Could be?
Old.
What is old?
The player itself.
Okay, so something is wrong with the CD player, right? But there's another possible reason why. Yes, ma'am. Right, so there's a defect in the CD, right? So those are the two hypotheses that we're going to work with. Now, let me see which one I have here first. Okay, so the first hypothesis that I have here is that the CD player is faulty. So as he said, you're going to test by experimentation. So what experiment would you suggest to test this particular hypothesis? Yes, ma'am.
Use another CD.
Use another CD?
Yeah.
To see the CD player is faulty. Yep, that's what I would do. So you're going to replace the CD with another one. And in this particular case, the sound from the second CD is okay. So basically the working theory for this is that the player has no problem, right? So that leads us now to the other hypothesis, which is, as somebody suggested, there's a defect in the original CD. So how would you test this particular hypothesis? Yes? Let me ask him this.
Try a new CD player?
Exactly. So basically, you're going to take that same CD and put it in the other CD player. And in this particular case, they observe that the sound still skips. So therefore, the working theory resulting from that is that basically the original CD has an effect, right? So you can see in this simple example how the scientific method works, right? And it works in this simple example, and it works in many other examples. And believe it or not, that's the reason why we have all the scientific discoveries that we experience and enjoy today, all right? Okay, so last thing I want to talk about here is, let me go back actually to the flow chart, because there's one thing I think is very important for me to emphasize. Now, let me just say, I don't know what your career goals are. I'm hoping that you'll all be scientists, or at least in the STEM field, because believe it or not, the country is very short in terms of the required number of STEM professionals that is needed now and also into the future. So I would encourage you to pursue STEM, science, technology, engineering, and math. And in fact, I'm the faculty sponsor for the STEM club here. If you want to join, shoot me an email because we plan to have some events to encourage students to pursue STEM careers. Anyway, I want to go back to this flow chart here because there's one important aspect which I kind of glossed over, but I want to spend some time talking about it. And that is this part right here. Now, if you recall, I said that after the hypothesis, you test your hypothesis by conducting an experiment, you get data, you look at your data to see if it falls in line with the hypothesis. If it doesn't, that means that you have to come back up here, make modifications to the hypothesis or come up with a new one and do the testing again and go back and forth, right? So the key thing I want to point out here is that when you get your data from your experiment and it does not line up with the hypothesis, you do not change the data to fit the hypothesis. You change the hypothesis to fit the data. Very important, right? Basically, if you change the data to fit the hypothesis, basically that's scientific malpractice. And depending on where you are and the type of research you do, there are serious consequences. With that said, let me give you a couple of examples. I have some URLs here to that leads to some news items. Whoops. Okay, let me do this here and go back up. So let me copy and paste this here. Okay, what did I do wrong? Let me go back here. Okay, so this was not a serious case, but I highlighted because I respect the scientist here. Her name is Frances Arnold. She won, along with two other chemists, a Nobel Prize in a field dealing with the enzymatic reactions of beta lactams. Not important for you to know that technical fact, but shortly after she won the Nobel Prize, and this was in 2018, shortly after a paper that she submitted. She was researching at the university, was published in a very prestigious journal called Science. Right, there are certain journals where, you know, if you have that on your resume and you go to apply to a college or university, they look at things like that, you know, your publishing record and so on, right? And the quality of the journal and the prestige of the journal itself, like Science, Journal of Organic Chemistry, and others, right? Nature is another one, right? It turned out that the data that was produced in that particular paper was not reproducible, which is very important in science. And actually is a big issue right now, especially in chemistry. I'm not sure about the other scientific disciplines. I'll talk about that later on. But it's a very big issue in terms of your credibility, right? Because whenever you publish results, right, you outline your experimental procedure and all of that, any scientist should be able to look at your paper and then conduct the same research and get pretty much the same result, right? If you have several scientists doing that and not getting the same result, then there's something wrong. And that's what happened in this particular case, right? And basically, she retracted the paper because, if I remember correctly, I think it's outlined here. She tried to find the notebooks, you know, where they record the data, couldn't find them. And therefore, as a result, she had to retract her paper, right? And as far as I know, that's the first instance of a person retracting their own research, all right? Oh, it's now 10:47. I'm having too much fun. Okay, so that's one good example of what should not happen, right? And I want you to look at the other example, which involves somebody actually going to jail, all right? Because they massaged their data to fit a certain result that they wanted, all right? Okay, so I was hoping that we'd be able to do this assignment in class, but since time has run out, I'm going to leave this assignment here. It's very simple. Let me put it on this chair right here. All right, so take it home, complete it, and I'm going to set a deadline date for you to submit it. Oh, let me collect the last page completed on your syllabus. So I'm going to create a Dropbox for this assignment. Make sure you do it. I'm going to leave some instructions to in the announcements for you to complete the assignment. All right. Thank you. Thank you. Thank you. Hello? Yes. Yes, I am. Thank you. Thank you. Thank you.
Will we print it all, you print it out or?
I usually print it out, but it's also available in Canvas.
Okay, I was just wondering if I should print out.
No, you don't have to. Hmm? Oh, yeah. Thank you. Thank you. Thank you. Thank you. Remember to send me that email.
Yes, sir.
Thank you. Thank you.
Just a quick question.
Yes, sir.
For me, like every Tuesday and Friday.
No, I meet another class on Tuesday.
Oh,
It's the same
that's what
course,
fine.
right?
I see it on the same.
Right, exactly.
Same place. So.
Yeah. Thank you. Oops, sorry. Thank you. Thank you. Thank you. Oh, no, I don't need the whole thing. I just need the last page.
I don't get my name. Not sure.
All right, hold on 1 minute. I should have done another round of roll call. What's your last name?
Al-Mahallawi.
How do you spell that?
Al.
Okay, it's not here. And I just printed this at 5 minutes to 8 this morning. So I don't know if things have changed. Did you do your registration?
Yeah, but I'm not.
When did you do it?
This morning.
Oh, okay. So it's probably I'll have to check and see.
Oh, okay.
Because I just printed this like,
Oh, okay.
early this morning.
Okay.
Yes, sir. What's your last name?
Ferguson.
Ferguson. Which spell that?
Tuggersson.
Ferguson, okay. I got it.
Yeah.
Hall. Okay. All right. Oh, you're right after me.
Yes.
Oh, I didn't realize. Okay, let me get out of here. You can log out. Oh, what am I doing? What's this here? You can close the page.